Now this one isn't heavy duty, but it's a counting problem nonetheless. And what we're supposed to do here is count the number of integers such that n-5 is a divisor of this quartic over here on the right. Now the quartic is missing a cubic and a square term, so we got to figure out how many values of n where n ranges through integers will that number be a divisor of this number right here. Okay. Now right off you can see there's at least one, right? And that one's quote obvious for n equals 6. If you choose n equals 6, it's very clear that this would evaluate to an integer, right? I mean, it's a knockoff, right? If you put a 6 right there, 6 minus 5 is 1. So you get 699 plus another integer, right? So we know there's at least one integer that does the trick, okay? But the question is, how do we actually find out all of them and conclusively state that that is all of them? Well, what you can do is a long division. And now I've done the work for you right here, and I guess I'd be remiss if I didn't show you how I did it. Long division is a little tedious. It turns out synthetic division is probably the best approach right here. So let's go ahead and run through that. Let's go ahead and write our numbers down here. So we got to put a 5 right here. All right, and then next we're just going to write down all of these coefficients. So this is a monic, so there's a 1 in front of n to the 4th. Now what we have going on here is there's a cubic and a square term that are missing, so we have to cover that by placing a 0 right here and right here. Okay, and then there's a 1 in front of the linear term, so we'll write a 1 there. And then 69 is the constant term, so we'll write that down. Okay, now the way I've always done this is you bring down, you got to leave a little bit of space here, but you bring down, thank goodness I left enough room there. So go ahead and bring this 1 down, okay? And I guess I've heard that called the drop down value, so we'll bring the 1 down. Now it turns out this row will be these coefficients right up here, okay? So what we do is we do 5 times 1 is 5, and you place it right there. And y'all, this process is called synthetic division. It's a lot simpler. It works for linear divisors than long division. Whoops! If you add that, that is 5 there. Sorry. Let me erase that. So we need that to be. That should be a 5. So let's go ahead. We're just adding right here, ladies and gentlemen. So you got 5 here. And again, you're doing addition. And now you're doing a simple multiplication. 5 times 5 is 25. Place it right there in this third column. Okay, add and you get 25. That's a 25 right there. Okay, and then when you do 5 times 25, you get 125 right here. You write small there, 125. Okay, folks, and that's 126 right here. Okay, and then if you do 5 times 26, is that 630? 5 times 126 is 630, so you put a 630 right here. Okay, y'all, I do hope this is legible. I think I've left enough space, and really when I start working, it's not enough. So that is 699. Again, folks, this is called synthetic division. And notice that's exactly this 1 right here corresponds to the coefficient of x cubed. 5 corresponds to the coefficient of n squared. 25, that's kind of ran into the 699 there, corresponds to the coefficient of the linear term, and 126 the constant term, and 699 is our remainder. And so that's where all of this came from, okay? Now, we caught a little bit of a break here because 699 is just almost a prime number. 699 only has divisors 1, 3, 233, and 699. And that takes some work to verify that it's prime, I guess. But anyway, it's almost prime. It's an almost a prime number. So anyway, we have plus or minus 1, plus or minus 3, plus or minus 233, and plus or minus 69. Now, right now, you could just argue, well, there is a solution for each one of these and be done, and that would be 8 solutions. Notice for n equals 6, that corresponded to 699 and 1, the factor 699 and 1 here. See? So for n equals 6, the factor 699 and 1 was what was at play here. But just for a concrete example, what if we set, let's say 699 over n minus 5 has to equal to some other divisor in the list there. Okay, because again, we've listed all the divisors, right? So we would just use, let's say, maybe you want to try 233. All right, well, yeah, okay, yeah, that's fine. We can use whatever we want. But you see, that would force n minus 5 to be what? 8, right? So that would mean that that would force n minus 5 to be equal to 3. Sorry, let me write this out more carefully. So n minus 5 would be equal to 3, since 3 and 233 are factor pairs. Okay, so n minus 5 is equal to 3. All right, and that would make 699 divided by 3 is 233, but that would imply that n is equal to 8, right? So 8 would be another solution. But I guess the bigger point I'm trying to make is that we don't have to solve all these out. We know each one of these will evaluate 2 integers. So I just did one of them right here, but that all I did was pick 233 and 3 out of this list, right? And so again, since there's 8 of these, there's 8 equations to be solved here, right? 8 equations to be solved. 2, 4, 6, 8, and we know that since these are divisors that will evaluate 2 integers, then we're done with the problem. That the answer is 8. Okay, 8 integers in, such that the conditions prevail. Now you may be wondering about the negative numbers, but like for example, you could do let's do a negative one in the list. Let's do 699. And again, none of this is required. If you just believe there are going to be solutions to each of these equations, we're done with the problem right now. Okay, there'll be 8 integers in that are guaranteed to satisfy each of these 8 equations right here. All right, but let's just try out. What do you want to try here? 699. Let's do a negative one. 699 over n minus 5. We'll say equals to minus 3, right? Okay. Now, what's that gonna? That's gonna require that this n minus 5 right here equals to what? Negative 233, right? Okay. 699 divided by minus 233 is negative 3, right? So what do we get right there, folks? That would be n, is that minus 228? N is equal to minus 228. So again, it would be totally counterproductive to go through all 8 of these. We saw one by inspection. We did this one, even though it's unnecessary. And we also did this one, just trying to illustrate what was really happening here and how these counting problems are kind of nice. If you can demonstrate a procedure that produces a count, you don't have to carry out all the computations individually. But again, ladies and gentlemen, there are 8 integers in that satisfy the conditions. If this had been natural numbers, it would cut this